Very nice, boy.
I'm researching that.
Okay.
BB.
We are set to BB.
We're beginning it right now?
But you don't have to do it again. Oh, there we go. Okay. Again, you turn it off because it's in my pocket. I go through the hospital's weird things. I guess I'll do this. Okay. So we say. So we know that there's no 2 in there apparently, but we're not sure about anything else. Well, no, we know those all are in there. The correct one is C, where it's the concentration times epsilon times C times the length of the tube. If you were to solve for epsilon, then we would have A divided by C L. But we're looking, the original formula is there. So, which of the following atoms will cause a molecule to have a 1-to-1 ratio of M and M plus M plus 2 plus and in the spectrum? Finish this before I finish the question. Brendan? Okay, we got 25. Now BR is the one that will give us a 1-to-1 ratio, M plus to M plus 2. CL will give us a 3-to-1 ratio. If you could read those masses, BR has a molecular, or an average mass of 79.9, and so it's 79 for half of them and 81 for half of them, so they average right around 80. For chlorine, your average mass is 35.45, for, let's see, 3 being 35 for every 1 being 37, so it averages to the half number. That can help you remember, if you can read those. In the molecule that has the following mass spectrum. nitrogen would be in this molecule. One thing to note is that you're never going to have your M+1 or M+2 be bigger than your M+. So some people look at this peak and say, oh, well, there's my M+, my M+1, and M+2. But your M+ is never going to be smaller than the next two over. So that's a double check there. Which of the following protons will have the furthest downfield signal in hydrogen 1 NMR?
Oh, crap.
Actually the correct answer here. Because oxygen directly connected to that carbon is more electron withdrawing, and it shifts that to a more downfield. No, downfield is higher numbers.
Okay.
Silly, mixed up nomenclature. So, what is the splitting pattern of see if you can get some here.
Wait, no, not stop it.
Okay, stop it. The majority of you said that one would be a triplet.
Sad face.
If we look at proton A, how many neighbors does it have? 2. And that will turn it into N+1 would be 3 for the triplet. Alright.
She meant to,
Next one.
but there were two.
What would be an approximate chemical shift range for the following carbon?
Oh, fuck. I can't do it this way.
Get back to another question.
Oh, so like a C now.
Okay. This one. There's
We only know it's not
the
A.
carbon of a carbonyl is the one that's most downfield in a carbon shift, so it's going to be 180 to 200. So which of the following methods gives the most information on the conductivity of a molecule?
I know.
because we can get the splitting patterns, which then tell us what the neighbors are, and we can kind of piece together the product. So the stretching frequency of the bond in wave numbers will increase when which of the following is true? One more. Anyone? There we go. So the force constant increases.
Logic told you that it had to be A. So it's exactly the same. Yes, that was my line.
There.
I don't understand why she asked me to show work.
It's not related to that.
Well,
So I moved the questions there.
yes, that would be one of the questions.
Oh, yeah. So we have this equation, when K increases, your wave numbers increase. If any of the masses increase, your wave numbers are going to decrease. On your reading, which of the following effects will raise the IR stretching of the frequency of a bond? One more. Oh, there we go. That's a good job. Close there, but B.
That was total gas.
Even if it's a slight majority. Okay. So you got your homework back, and overall,
Except that when she took off that one, I'm still upset about that.
we got
Why don't you show her
one
how it
thing to pay
calculates?
attention to, I saw a few times, is when you're doing that rule of 13 and then you do the U, you need to be careful. The rule of 13 is you get your N plus R over 13, and then your U is equal to N minus R plus 2 divided by 2. So make sure that these numbers correlate. Some people were trying to use, after you put this in the formula,
I know, but just do it.
and they would use this number instead because they were thinking it was the number of hydrogens. So we actually stick with these two numbers before you plug them into the molecular formula to get your units of unsaturation. So pay attention to that. Any other questions on your homework? I guess I have to open up class. What's your Haley?
I had a question about the IR on the board. How do you know if something is that is a vitamine or it's a SB2 carbon?
So we'll go into that actually in more detail today. We'll talk about those stretches a lot more today. So hopefully I can answer that question. Your homework for Friday is posted, and there are two ways that you're supposed to calculate the, or use this formula. One is to calculate the wave numbers based on a force constant that you look up in the CRC. And if you look in the index for force constant, you should be able to find the table in the CRC handbook. Alternatively, you're given a wave number and the masses, and you need to calculate K based on that. So you'll want to rearrange this equation to solve for K. Someone asked a question about the reduced mass on Monday, and without going too far into the physics of it, it's a way that they take a two-body system where you have two springs, and they combine them together to effectively make it one mass instead of two, so you have just one thing you're calculating. There's actually some complex theorem behind it. I didn't don't want to go into that into detail, but it's effectively treating that whole thing as one unit instead of two separate units. And if you want, you can look that up together if you want more information.
Just to hear you, it's fine.
So we stopped right about, we're finishing up our vibration frequency calculations. So we stopped right about here. Just want to talk a little bit about the two different setups of a spectrometer. The original setup would be our dispersive IR, where you would take your sample and put it in, and there would be your infrared energy source. There's a mirror that splits that beam into two, and then one part of the beam goes through your sample cell and the other goes through your reference up at the top. And there's what's called a beam chopper, which is basically sliding back and forth so you can get each beam at different times. And so at one point it's recording your reference cell, and at one point it's recording your sample cell. And it alternates back and forth, and it does the subtraction, and then you get what's actually passing through you and what's being transmitted through the sample by that subtraction. And then there is a slit, and there's a diffraction grating. This diffraction grating is going to slightly rotate back and forth, and depending on the angle it is, different wavelengths of light are going to go through that final slit up there. And so as you move one way, the longer wavelengths are going to come through. If you move the other way, your shorter wavelengths are going to go through. In order to record the entire spectrum, you're going to have to move through the entire frequencies, and it's going to record it at each point. Essentially, this gives you one scan. You scan at each wavelength and record what's coming out. The more modern technique is to use what we call a Fourier transform IR, where you have your infrared source, it splits the beam, and part of the beam again goes up into what we call the reference, and one is going to be into the sample. But these are going to have different times that they're coming through, and so the computer can tell the difference between your reference and your sample scan based on the time it takes for that to come through. And then the detector is going to detect everything, and it's going to give you a very complex signal, which is the interferogram here, which essentially looks like one peak. I think this is added from what you had. Okay. So all at once, all the wavelengths of light are being shined on your sample. Then you can see in this example there are two wavelengths of light. They can either add or subtract together to give a signal. And the one below is the two added together. And if they can either add constructively or destructively, and you get this complex signal. The computer then takes that and can split that out. We don't do that. Obviously, the computer does this for us. Then It's also going to compare your, so the unmodified interferogram would be your reference sample, and then we have the absorbing sample, which is going to be slightly different. The computer is going to say, there's a difference between these two signals, which means that these are the two peaks that are showing up on the infrared spectrum. So it's kind of the Fourier transform in a very short nutshell, or very small nutshell, I guess. The signal that we get out, I don't think I have any, but they are going to be very complex because that's just looking at two waves. If you look at the entire spectrum from 4,000 down to 400, we're going to have every single one of those, depending on how many, let's say we do one wavelength increments, you're looking at almost 4,000 different wavelengths, and your computer is going to deconvolute all of that and give us what we look at typically for the spectrum. So again, we saw this before, but you can look at these in either the transmittance or the absorbance. And your transmittance is the percent transmittance is equal to your sample divided by your reference, or the intensity of light coming out through your sample divided by the intensity of light coming through your reference, times 100 to give us a percentage. And generally, this is from the NIST database, but generally we go from 0 to 100%. They're actually not multiplied by 100 on their scale, but it's the same type of scale that we look at. The NIST website will give you either transmittance or absorbance. So this is phenol in both of these spectra. And the bottom one is our absorbance, which is our negative log of the percent transmittance divided by 100. And we talked about that a little bit, but essentially some of your bigger peaks aren't quite as intense when you do the negative log. And you can see some of the littler peaks there as well. Generally, we are looking at the percent transmittance, but I just want you to be aware that if you find one that is an absorbance, that's how that compares. Just same wavelengths, but they're going to be positive peaks rather than negative peaks. Here's the simplified chart from your book. This is table 2.3. These are ranges that you probably should know. We are going to be more specifically, we will look at most of these, but the key regions that are most helpful in interpreting these will be your carbonyl region, your alpine region, our alcohols and our phenols, and then our CH groups. So, as a general rule, I tend to look at this alcohol amine section first, then I'll look at the carbonyl section, alkenes, and then also the CH region to interpret. That's just kind of my general strategy when I'm looking at spectra. There are a lot of numbers on here, and so table 2.4 is the base values for each of the very common functional groups that we're going to be encountering. These numbers you just need to know. The other ones you may not know every single one of those ranges, but you should know how different where the relative ketones and esters and everything fall within the range of carbonyls, but maybe not the exact range of, say, amines. If you have the bend 1640 to 1550. So both of those are tables directly out of your textbook. This is kind of an idea, if you're not sure where to get started on an IR, here's a way that you can go through and do the interpretation. So again, I said, looking at the amine phenol section, so you could say, is there something within that 3300 to 3500? Yes or no? If yes, well, is it broad and strong? Yes, that's likely an OH. If no, it's either going to be an amine or a alkyne hydrogen. If it's an amine, is it primary or secondary? So it's kind of just a checklist you can go through, or a flow chart in your head. And then you can look at the CH region and some carbonyls and carbon-carbon double bonds. I think this is a typo here. So this should be really 1850 through about 1600 total. And if you're looking in that region, determining whether it's strong or weak may help you to identify the alkene versus the carbonyl. If it's a carbonyl, we're going to want to look at other pieces of the functional group. So is there a peak? Here's the relative range for an amide, but then we also want to look and see if that correlates with other parts of an amide. If it's a primary or secondary amide, you're going to see the NH peaks, and so we'll do some correlation there. So just a general strategy, and that's a little bit what we'll do today. And the very similar thing here, saying what's most important? Your OH, your NH, then your carbonyl, then those triple bonds, and then we'll start looking at the nitty-gritty details for more interpretation. So start with what is most important and work your way down. So let's get into the nitty-gritty details. We're going to start with the hydrogen atom, meaning not carbon. And then we're going to go into the carbon hydrogen and multiple bonds, the aromatic stuff, your carbon nitrogen, and then carbon oxygen. Likely we won't get through all of this. This is actually the bulk of the interpretation that we will need to do for the IR. There's going to be some miscellaneous ones we're going to go over also on Friday, but some of this is going to bleed into Friday as well. And don't forget that your homework is due on Friday. That's all the announcements. So, almost all of my slides today are just spectra. So we're going to start out looking at the hydrogen atom bonds. So we're going to start with our OH bonds. Now we know that our general range for the OH bonds were from about 3,400 to 3,300. It may extend outside of that range, but that's our general range for where we're going to see the OH peak. But in most of our spectra, we are going to see very broad peaks. This actually depends on how the sample is prepared. If this is a neat sample of your material, which means that it is your molecule only, and a salt plate would be considered a neat preparation, then you're going to get your alcohols hydrogen bonding with other molecules of the alcohol, and you're going to form the hydrogen bond network between all of those OH groups. This will do two things. One, it's going to actually lower it from what it would be if it was just an OH, and it's going to make it more broad. So hydrogen bonding will lower the stretching frequency and make it more broad. If we look at this hydrogen bond, there is some donation of this hydrogen to the oxygen. That means that we are going to slightly weaken the OH bond within the molecule. And that's going to vary depending on how much hydrogen bonding is going on, and different molecules within your sample are going to have various hydrogen bond strengths, so you're going to have that broader peak because some of them will be a little bit more weakened, some are going to be not quite as weakened, and you're going to get a really broad spectrum for that OH. On the other hand, if you have an alcohol that is is prepared in solution, so say you took a solvent that wouldn't absorb in any of these regions, typically carbon tetrachloride, so CCl4, we added CCl4, then you're going to dilute out those alcohols and they won't be encountering each other quite as much, so they're not going to be hydrogen bonding. This is going to give us what the actual OH peak would look like if it wasn't hydrogen bonding. And we can actually see that there are two peaks in here now. This really sharp peak up around 33, no, that's the 36, 38. And that is corresponding to the free OH, not hydrogen bonding at all. You can see that it is very sharp and higher in frequency compared to the hydrogen bonded OH. So our typical range for those is going to be 3650 to 3600 centimeters to the -1, and it's going to be very sharp. This is something you'll want to pay attention to if you're collecting samples. If you're running your own IR, we typically run neat samples, but if you're having to do them in solution, you might observe this effect. Or if you're getting samples, or spectra I should say, off of SDBS, they have sometimes multiple IR spectra, some of them in neat solution, some of them is a KBr pellet, some of them as a solution, and if you flip through those you can see the changes. Both of these are the same molecule, SDBS, on SDBS, but they have different patterns or different preparations. These are actually both butanol, one butanol. As I mentioned, the one on the left here is in carbon tetrachloride, and the one on the right is our free alcohol, or neat alcohol, I should say. So we have two peaks here for the OH, not hydrogen bonded, and if it's not quite dilute enough, you're still going to get the OH that's hydrogen bonded. We also see our sp3 CHs, which we'll get into a little bit more detail in a little bit. And same here, this is our OH, which is hydrogen bonded. And these are sp3 CHs. there's not a whole lot else to this molecule. And we'll get into interpreting the rest of those peaks in the fingerprint as we come to the CH groups, which we'll get to in a little bit. So those are the key points we want to look at the moment. Any questions on that?
I'm sorry, I'm confused. That doesn't mean that there's two oxygens, does it, present in the molecule?
Mm-mm.
It just, depending on what solution you run it in?
Yep.
Okay.
Yep. Yeah, this isn't saying that there are two oxygens. It's also not saying that there's an oxygen and an alkyne or an amine or something like this. This is just an artifact of the way it was prepared. This is one of the reasons why you have to be very careful not to overinterpret an NMR, or IR. We will definitely overinterpret our NMRs. So that's the alcohol. We also want to look at the OH that corresponds with a carboxylic acid. Your carboxylic acid is very broad. So we're looking at about 3,400 down to 2,400 meters to the -1. And very broad in this OH. This carboxylic acid has the extreme of hydrogen bonding. So in a sample of a carboxylic acid, you're going to have an OH and an oxygen that's double bonded, and you can set up two carboxylic acids so that they parallel one another in terms of hydrogen bonding. So here we have a hydrogen bond donor next to a hydrogen bond acceptor, so we can do a hydrogen bond between those two. And here we have the hydrogen bond acceptor from the first molecule going to the hydrogen bond donor of the second molecule. And we call this a dimer because you have two of them hydrogen bonding to each other. This, again, is going to weaken the OH bond to some degree, and you get a wide range of these hydrogen bonding, and we get a very broad OH peak in our IR spectrum. So all of this is coming from the OH, although there is, at the top, a little bit more jaggedness. This is coming from our sp3 CHs that are being buried underneath the OH, but they still absorb a little bit, and they show up as additional peaks on top of that OH. Now, in order to confirm that this is a carboxylic acid, we would want to look at the carbonyl, because a carboxylic acid always has a carbonyl associated with it. So we should see a CO peak, which we see a peak at 1712 for the carbonyl of the carboxylic acid. And always look for that for confirmation that it is a carboxylic acid. Questions on that? All right, we can move on to the amines then. I added a couple extra spectra to the slide this morning, so I didn't get those on your updated slides. I apologize. The first one up in the top right corner is the one that you have on your slides. If we look at amines, there's different levels or degrees of substitution that we can see in the IR and our structures. So generally, your NH is going to show up between 3,500 and 3,300. Weird numbers. We can look at the number of peaks within that region to try and determine whether it's a primary, secondary, or lack thereof being peaks two bands because there's two different hydrogens, and that is the case, but it's not the individual bonds we're looking at. We're actually looking at whether those two hydrogens are in the symmetrical type of stretch or the asymmetrical type of stretch. And so those two come from the asymmetrical and the symmetric stretches. The asymmetric is the higher energy and wave number, and the symmetric is the lower wave number or energy. And we see that in our first IR here. This is butylamine. So we have the NH2 group, so this would be your NH2 asymmetric stretch. And this one is going to be the NH2 symmetric stretch. If you notice, on the side of the NH2, the two peaks there, there's a slight shoulder, a little bit of a bump out, which is right here. This is an overtone of our NH bending in the molecule. And you'll tend to see those in your secondary amines in particular. In the primary amine, we're going to see only one peak. Or sorry, now we're moving on to the secondary. So in the secondary amine, you have R2 and H. We're going to see one band or one peak for that NH stretch. And then if you had a tertiary amine, we now no longer have any hydrogens on the nitrogen, so you're not going to see any bands at all. The spectrum on the left here has the secondary amine, and I've just blown it up to the section we're talking about at the moment. And you can see that there's really that one peak there, but it is kind of a little bit broader underneath, and part of that is overtones from other parts of the molecule. And your NH peaks, especially if they are secondary and they're aliphatic, meaning they're not connected to an aromatic ring, are pretty weak, and so they don't always show up very well. The aromatic secondary amine I have on here, the aniline, has the two NH stretches for our asymmetric and our symmetric stretches. And then you can actually see very clearly here that overtone of the NH bend. So be careful when you're interpreting that region, because if you see three peaks in there, it may start confusing you. Speaking of the NH bends, those are going to show up lower. Remember that stretching frequencies are going to be higher wave numbers, and our bending frequencies are going to be lower. And the NH bends, and these are best in the primary. So your RNH2, you're going to see this in the bend of these two in a scissoring bend with the hydrogens going back and forth. And that range is about 1640 to 1560. And these can be anywhere from medium to strong in intensity. If we look at the butylamine here, we see a peak at about 16 or 1606, it looks like. And that is our NH2 bend for this molecule. And that corresponds with that shoulder being 2 times because it's the overtone of that NH2 bend. And the shoulder is somewhere right around a little bit less than that, maybe about 3,200 there. In the aniline down here, we see the peak for that is a little bit lower. This is your NH2 bend. In the anilines, they tend to be a little bit lower, maybe around 1,500. Actually, it might be one of the lower ones. That's probably this one here. Yes?
I'm a little confused of why it shows up as a bend, and then it's not showing up as a bend when it's above 3,000, the NH2.
Okay,
So let's throw the overtone on this one.
so the definition of the overtone is when you excite not to the first level but to the second level, and that is 2 times the energy. And typically, so if we're looking at this being 1,500, we're going to see a peak about 30 or 3,000 or a little higher than that. And so that would be your NH bend overtone.
Okay.
So we've got an NH bend that's showing up about 1,600. Then we're seeing another peak for the NH2 overtone of the bend. But we also see the stretches in that same region. In this one, we have several peaks within that 15 to 16 region because we do also have some aromatic. So we have our CC of an aromatic ring. And we also have that NH bend, which if I'm interpreting this, the overtone of our NH bend is at 3,200, so I think it is actually this 1,600, which is half of that 3,200 to assign to the NH bend. And the aromatic one is going to be like for that peak, and this one, and that one. So notice those show up in the exact same region as what we've been interpreting with our aromatic C double bond region. So it makes interpreting those a little bit more challenging. You gotta be careful with those. For the aliphatic ones, they tend to be a little bit broader. So you can see here we've got a little bit more of a broader peak, but they don't necessarily have to be broad. Other questions on that? Okay. Well, now we'll go back into a little bit more of the familiar territory with the CHs. If we look at this simple CH compound, this is hexane. And all we have are carbon and hydrogens. These are going to have your CH bonds in the sp3 hybridized CH. And those are going to be less than 3,000 centimeters, generally somewhere between 3,000 to 2840. centimeters for those sp3 hybridized CHs. And when you have a molecule like hexanes, you have various ones. You've got CH2s, you've got CH3s, so we're going to see several peaks within that region right below 3000. So we have our sp3 hybridized CHs, whole group of them there. But we have a couple other things. Mackenzie, did you have a question?
Yeah, is that a stretch or a bend, or does it matter?
That's a stretch. These are stretches, yes. Within the molecule, we also have the ability to do the bending, and so we're going to analyze that on this simple compound because there's not a whole lot of other things interfering. These often get messed in with everything else because they are in our fingerprint region, that 1500 and below mark, and so we can see them with our simple compounds, but they're add some complexity to other more complicated molecules. So if you have a CH2 that's bending and it's doing the scissors, so your CH2 is coming back and forth, this is going to show up at approximately 1460 millimeters to the -1. You're also going to see a CH3 bend. And this is the asymmetric. And that is also going to be about 1450 or 1460. So these two tend to overlap. The CH3 bend in a symmetric sense is at about 1375, so that's distinct from the other two, and should show up. Then you may also see a long chain of carbons where you have 4 plus carbons, and what we call concerted rocking. So if your entire row was a group of CH2 groups and you were all rocking together, we would be getting into the 720 centimeter range. And these tend to be weak to medium in strength, so they may or may not show up very well. So in this hexane, we can see 2 peaks here. So this is our CH2 bend plus our CH3 bend, likely, from the asymmetric. And then our CH3 bend that is symmetric at the lower wave number here, it's about 1379. And then this little guy over here is our long chain rocking. And you can see that it's a very weak stretch, and if you had anything else in your molecule, you're not going to be able to interpret that. And within our CH2 and our CH3 bending, that's right in the region of our alkenes and things like that. So we are adding some of the complexity into these IRs. Okay, that's all we have time for today.